Podcast, I'm going to address lipids and their characteristics and how we classify them. So text references there, 68 to 71, trying to describe here characteristics of lipids in general, and then characteristics of triglycerides, characteristics of phospholipids, and then characteristics of the steroids. And of course, then this gives us the biological importance of the three groups of lipids. There they are again: triglycerides, phospholipids, and the steroids. So let's jump right into this here and talk about, in general, lipids are nonpolar. This is because they do not have a lot of oxygen. So this is lack oxygen in their structure. So nonpolar, lack oxygen. And the first of three categories here are triglycerides. They are fats and oils resulting from the condensation of two parts here: glycerol, and number two, or number B, fatty acids. So first, let's take a look at this glycerol molecule here. A glycerol molecule is a 3-carbon compound, 1, 2, 3 carbons here. And you see hydroxyl groups on either side, and then surrounded by hydrogens here around. So this is the glycerol. And then the fatty acid, the fatty part of this is the nonpolar part here. And again, this is simply a hydrocarbon chain. There's not a lot of oxygen. If any, there's no oxygen in a hydrocarbon chain. In fact, there's just carbon and hydrogens in a hydrocarbon chain. No oxygen whatsoever. So because there's just carbon and hydrogen and no oxygen, this makes it nonpolar. Again, oxygen is an extremely electronegative element, and that's going to generate polar covalent bonds. But because there's no oxygen in this fatty acid, in this fatty part here, it means it's nonpolar. These are nonpolar covalent bonds. So if you look up in the yellow part of this here, right, we see this hydrocarbon chain, right? Carbon, 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 and there's hydrogens surrounding those carbons. There should be a hydrogen on the end right there, but it looks like I got it cut off by mistake. On the other end of the fatty acid is what makes it an acid part here. This acid part is due to the fact that there's a carboxyl group on that other end. Right? So here's a carbon, double bonded oxygen to the hydroxyl there. So I know you're saying, you're like, well, look, there's oxygen right there. Yeah, I know, but like the fatty nonpolar part of this, there's so many of these carbons here, and this is 14 to a couple dozen of these, depending on the different type of fatty acid. And so you've got an overwhelmingly much more nonpolar region than you do polar regions. Plus then too, this is going to then result in this ester linkage, which you don't have to know this ester. This is another functional group, but when you go to college and take organic, then you have the pleasure of memorizing that. But suffice it to say, we are able to put 3 fatty acid tails, 1, 2, 3 fatty acids onto this glycerol molecule. And this is why this thing is a triglyceride. Tri meaning referring to then the 3 fatty acids, and then the glyceride referring to, of course, the glycerol molecule. So if you're just, talking about this quickly with some friends at lunch, you diagram it just like this, right? And this looks like the letter E, where this would be the glycerol molecule, and then this would be the fatty acid, fatty acid, fatty acid. Okay? So these triglycerides are, again, fats and oils. Primary role here is energy storage. This is how cells, right, are storing excess energy, right? Look at all the covalent bonds, right? Potential energy, potential energy, potential energy, potential energy, potential energy, potential energy, potential energy. I think you get the point. There's lots of bonds there, all right? Energy storage, right, in the bonds of the triglyceride. Right? So if we look here for a second, you have to know the difference here between a saturated fatty acid and an unsaturated fatty acid. The saturated fatty acids have all single bonds between the carbons of the hydrocarbon chain, and unsaturated fatty acids, by definition, have at least one double bond between some of the carbons in the hydrocarbon chain. This double bond right here gives it a different characteristic than all these single bonds. The characteristic of saturated fatty acids is that they tend to be more solid at room temperature, right? You look at the examples up here, right? Butter, 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 and I know that butter makes everything better, but not always. So the saturated fats here, due to these single bonds. Unsaturated fats get you them being oil, right? So this lowers, these have a lower freezing point. Lower freezing point, they're more liquidy at room temperature, right? Because of that double bond. Why? Because it is that way. That's chemistry. Physical chemistry, we can talk about that later. You've heard of saturated fatty acids and unsaturated fatty acids. Maybe you've heard of omega-3 fatty acids, and the omega-3 fatty acids here, due to the fact that this is the omega part of this, and then this would be a carbon, and then here's the third. At this third carbon, between the third and the fourth, there's a double bond, and a double bond, and a double bond. So these omega-3 fatty acids, or omega-369, right? You see these in fish oils. Right? And so some people take this, and there's purported health benefits to this. But again, this is the rationale behind, or if you've heard of omega-3 fatty acids, this is why they are unsaturated fats there. At the bottom part of this, looking at a saturated, so this is just the cartoon of the saturated, and then here we have the carbon, and the single bond between them. So there's a saturated fatty acid. The unsaturated comes in two different flavors here, this cis isomer and this trans isomer. And the only reason I bring this up is because you may have heard of trans fats, and foods that are high in trans fats, they're not very good for you. So why? Well, let's go back to this and just look at the structure for a second. Here's the cis, right? And here's your double bond. And this cis conformation means that the hydrogens are on the same side of this double bond. The trans conformation here has the hydrogens on opposite sides, trans across, right, that double bond. But look what that does, right? This trans one, right? Look at this trans structure here, right? Does it look like this unsaturated, or does it look like this saturated? Well, it looks like this saturated one. So it's going to behave more like saturated fats. So this is why trans fats are not necessarily all that good for you, is because they look similar to these unsaturated, and they're going to behave similarly as well. So that's what's going on there with the cis and the trans, and the unsaturated versus saturated. So if we look at this triglyceride, we're going to move away from the triglycerides now and talk about phospholipids. But the phospholipids are similar to the triglycerides in that there's going to be glycerol and fatty acids, but there's only two fatty acid tails. So here I've kind of turned this diagram on the left here on its side, though. And so phospholipids are the second class of lipids here. They are, look at it, how I titled this, modified triglycerides with the polar regions and non-polar regions. So let's pick out what we know. Well, here's our fatty acids, right? So this one, this fatty acid tail, since it has this double bond and this kink in it, right? This is unsaturated, and then this one up here would be saturated. And then here's our glycerol molecule, and this is a little tough to see, but here's the glycerol, right? These three carbons right there. And then I got one fatty acid coming off and another fatty acid off of there. So you can see how this is sort of like a triglyceride, except for the fact that it's not a tri. We have 1, 2, and then we take one of those fatty acids off and we put on there this phosphate group, which has a negative charge to it, and then we put this choline group thing on here, and this is going to have a positive charge area to it. So by bonding this choline and this phosphate to the glycerol instead of a third fatty acid, you generate this area of polarity here where there's a negatively charged area and a positively charged area. And so this is how you get a phospholipid, right? The phospho being here, and the lipid part, again, being the saturated and unsaturated tails. So this is a space-filling model. Down here is a cartoon version of it, where this hydrophilic head right here represents the negative and positively charged areas of the phosphate. This is the phosphate and the choline, right? And these parts are going to interact with water, right? This is what makes them hydrophilic, right? Will interact with water because water is a polar molecule. These hydrophobic tails over here are nonpolar, right? Nonpolar will not interact with water. And so phospholipids are primary components of all membranes. So we get these phospholipid bilayers forming, right, in membranes. So membranes of cells, membranes of organelles within eukaryotic cells are all phospholipid bilayers. It gets more complex than that, but suffice it to say, this is where we are at the moment. So we've got triglycerides, we've got phospholipids, and now the third characteristic here, third grouping of lipids are these steroids. So this is group number 3. The steroids are unique lipids based off structure of cholesterol. So these have nothing to do with triglycerides or the phospholipid. They don't look anything like that. Right? So structure based off cholesterol. So here's cholesterol, and we see this kind of hexagon, 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 pentagon pattern here, where all steroids have this basic hexagon, 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 pentagon structure to them. But then the orientation and the variation of the functional groups that are attached to that hexagon, 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 pentagon thing, I think I'll just start referring to this as the polygon base here, the polygon base. That's going to change how the steroids react or function. For example, here we see cholesterol, and at this carbon right here, there's a hydroxyl group, and at this carbon, there's a methyl group, right? And cholesterol is in our diet. Hopefully not a lot of it, but we do need some of it, and this is why, because we take this cholesterol into our diets, assuming that we are animals. Plants have ways of generating these molecules photosynthetically or are met with other metabolic reactions, right? So animals and plants generating this cholesterol, and from there, in animals, for an example, we make these steroids. Cortisol is one, and you see that cortisol, again, here's the polygon base there, but then at this carbon, instead of there being a hydroxyl group, there is this double bonded oxygen, right? And instead of there not being a double bond right there, now there's a double bond right there. So by changing what's around that polygon base, you get different types of steroids, right? Cortisol is one, aldosterone is another one. Here we have testosterone, estradiol, progesterone, and you see that they're all have that polygon base. Vitamin D over on the left here, final example, is sort of very highly modified, right? But you can see where that polygon base might have been, even though it's not, there. In that part, you still have that polygon base, and then things branching off of that. So again, there are our lipids, triglycerides, phospholipids, and steroids. You can, I don't know if I gave you this, but you can kind of sort of create a graphic organizer to summarize everything there for you. Okay? Hope that was helpful, and see you in class.